Hope everyone's having a good SharkFest so far. Today, in this session, we're going to talk about TCP tricks, some tips, and also a couple of case studies. So, before I get into the actual content, just want to take a moment to introduce myself. My name is Greer. I work for a company called Packet Pioneer. So primarily a training and professional services company, but I like to go in and help people resolve problems. I'm definitely on the performance side rather than the security side. So as you'll notice in several of the trace files that I'm going to show you, what the problem was or the complaint was, the whole reason why we were capturing in the first place is because things were slow. So the complaint is slowness, or the network's slow, we all hear that a lot. But what was the root cause, and what did we do to resolve it? You might also find some of the writings that I do, some of the articles that I write up on webmytool.com. If you haven't been out there, it's a great site for network analysis and troubleshooting. It's like a blog that's really focused on what we're all interested in, that is network analysis. You can also see some Bright Talk sessions from time to time if you go out there. I do them on general packet analysis, Wireshark analysis. They're about 45 minutes to an hour, just where we share a war story or share a new thing that we learned from a certain situation, or just some general tips and tricks with Wireshark. So you can also go out there from time to time. Okay, let's get right into the content. So let's talk about TCP. Why are we here talking about TCP today? Why is there such an interest specifically in this room about this protocol? Well, important stuff uses it, right? It's a reliable protocol. If we have a business critical application, it's likely running over TCP. So it's a protocol that all of us want to become familiar with, very familiar with. It's carrying important data. It has a behavior. When it's misbehaving, we can tell with a product like Wireshark, but it really helps us to steer our troubleshooting into the right area, to the real problem domain. Also, some problems, I like to say, they hide at this layer. All right, and I'm going to show you why in just a minute. But I know for me, a lot of times when I get called to come in to help troubleshoot a problem, much of the time it's something related to TCP. Or TCP is what steers us in the right direction. So the more comfortable, the more of an expert you become at this protocol, the better troubleshooter you're going to be for what we're trying to do, and that is to resolve problems. And also, I find more and more, this bottom bullet's true. Few people today in IT organizations take responsibility for it. But let's talk about what I mean by that. First of all, when a problem strikes on a network, and again, I'm coming from a performance perspective, things are slow or not operating as optimally as they should be. When a problem strikes, and if we're a network engineer, if we put on our network engineer hat, that's my responsibility, that's my job description. I'm sure many of us come from that background, or that we have that role today. So when a problem strikes, that network engineer, according to his job description, he's going to try to exonerate these lower layers. He's going to make sure that his pathways are good. He's going to make sure his switches and routers on some screen, LCD screen in the data center show green. He doesn't have anything down. He has no outages. Make sure that his routing tables are good, making sure that he isn't slamming some link, his capacity looks okay. So he's going to take absolute responsibility for the network layer, the data link layer, the physical layer, the wireless environment. And we could say that his job description says that those are his layers that he's responsible for. Now, some of us know that it goes beyond that, right? Some of us would say, oh, I'm responsible for all 7. However, for this role, from this perspective within IT, this is what we find. Layer 1, 2, 3, that's me, I'm the network guy. Okay, but what if we find a different type of problem let me back up a second. So primarily what I've seen is network engineers, they go in there and try to exonerate the network, right? They want to prove that it's not the network. And that makes a lot of sense. They've received a lot of heat over the past decade or so, right? People say when it's slow, it's the network. We hear it all the time. In fact, we hear that coming in from end users. Well, end users don't know much beyond their Linksys router at home. They don't know what networks are doing. But still, even they get involved. They might even call into the help desk and say the network's slow. The help desk person then says, okay, yeah, the network's slow. Hey, network engineer, why is your network slow? We even hear when we call into like a call center, if you're calling your bank and you just need help with a bank account, and their system is slow that day, that person receiving the call, wherever that call is from, they might pick up the phone and say, hey, our system's slow today, the network's slow. I heard someone say that a few weeks ago, and sure enough, on the other end of the phone, I'm thinking, how do you know that your network is slow? You're just taking calls on a call center, right? Because it's become a culture. People blame the network. So a lot of times, as network engineers, we go into defense mode. I want to prove that it's not the network. I've got good throughput. I don't have any packet loss. It's not my problem. Now the opposite, if we're from the server app side of the house, our responsibility is keeping the applications up and running, making sure they're configured properly, bringing up servers. Well, I would say that my responsibility, I'm in the upper layers. The network, once it leaves my server environment, it's on the network, it's not my problem. However, within my server environment, that's what I control. Patching servers, making sure the services are running as they should, making sure my servers have enough resource. However, I like to blame the network because a lot of times I can show a little chart that shows green. It looks like my server is resourced properly, my services are active, I'm supporting hosts. Servers look great. Do you notice a layer that seems to be missing from either bucket? This is what causes a lot of contention. These two guys, they start finger pointing at each other. It's your fault, it's your fault. They're jumping over this layer that's in the middle. The transport layer. Nobody really seems to want to own it today. Because if you think about it from a network perspective, should we own the transport layer? Some would say yes, some would say no. When you think about it, TCP is a stack on a server or on a client. The network itself doesn't generate that component of the stack. It might manipulate it. You'll see that one more. However, should I own, as a network person, TCP? Some would say no. In fact, in the environments where the network engineers say no, well, this is where they start to point fingers a lot of times. So I find personally, and when I'm out there consulting, I find this in several conference rooms. People are fighting over what's causing the problem. They're tossing the hot potato back and forth. But when we take a look at it, I'm not saying all problems are here, but it's definitely one of the keys that we can use to figure out, do we go up the stack or we go down the stack to resolve the problem? Okay, and I'm going to show you what I mean by that. Also, we find, what if the problem is in neither camp? What if it genuinely isn't a server problem, or it's not the network itself? What if it is within TCP? This is why we need to become better TCP experts, because we find more and more today, this is where problems can hide. Okay, let me show you an example of what I'm talking about. I'm going to bring up a trace file. This is from a friend of mine who is doing a backup of one of his servers. And just to tell you just a little bit about the environment before we dig into the packets, he had one server that was backing itself up, so primary to a backup server. These guys were on the same switch, same blade. It's not like we were crossing a network environment to get from the primary server to the backup server. They were gig attached, and he would begin this backup process as soon as his shift ended. So at about 5 o'clock, he would start the backup process, and this backup, as the database grew, and as the amount of data being transferred from one server to another grew, it took longer and longer and longer to move this data from A to B. Well, finally, it began taking so long to move this data from the primary to the backup that it began to spill over into the next business day. So it was taking over 8 hours for him to move a database which wasn't very big. As I recall, it was only in the 100 gig range, from one server to another. But both of these servers are attached to the same physical switch, and they're gig attached. Now, if we do the math on that, let's just use the 100 gigabytes for example. If I'm moving a 100 gigabyte database from one server to another server, and both are gigabit attached, how much time should that take? I'm moving 100 gigabytes. That means it's 800 gigabits. And if I'm line rate, if I'm blowing that thing across at 1 gigabit per second, it's 800 seconds, right? Divide that by 60 in what, 7, 8 minutes ish? How many minutes? 13 minutes. I'm sorry, you're right. 360. Yep, good. 13 minutes. 15 minutes. Let's do that good measure. You know what? Half hour. This thing was taking 8 hours. Now, of course, what are they blaming? The network's slow. Well, here he's like, okay, I've got 2 switch ports, literally same blade, one going to one server, one going to the next. Very minimal network. There's no Ethernet errors on these ports. He measures the amount of traffic. It's not a tremendous amount. It doesn't look like things are being, like things are going up above a certain capacity level. There was 0 configuration as far as rate limiting or anything like that on this thing. Very simple configuration. Of course, blaming the network. So this was a sample trace file from it. Now what I'd like it to do is remember that the complaint was time, right? How much time is it taking to move this data from one server to the other? So in Wireshark, 2 columns we always want to have available to us, especially if we're troubleshooting performance. We want to have our time, which personally I like to keep that my running total. So packet number 1 is 0000, and then I got my running total time. And next to that, we got our delta time, delta displays. Basically the amount of time since the previous packet, end of packet to end of packet, between those packets you could say. Okay, so I have that set up here, and I'm interested in time. So what I'm going to do is I'm going to scroll. I'm going to keep my eye on this column, the delta time. Because I want to see, when do I see it jump? Now we got to take this in context as well, because if I take a look at packet 13, all right, I've got 0.000123. That represents 123 microseconds. This thing is blowing traffic, and things are looking good right now. If you look at the direction that traffic is going, all right, we have 192.168.1.2 and .1. We've got our length, packet length, right? These are full-size packets. Traffic is going from .1 and it's going to .2. So the primary is .1, the backup server is .2. We're moving data from one point to another. Now let's take a look at when does traffic start to slow, or when do I start to see a delay of some kind. That's what my eyes are going to look for as I scroll through. Now there's a couple other graphs I'm going to show you in a minute here, but first let's start here. I'm just scrolling down. What I'm looking for is when do I see a shift in delta. I could also sort the delta column as well. We'll just do this the manual way for the first time. If I come down, I'm looking, and I'm going to go by page. All right, you see on 140, 20 milliseconds. It's going back the other way, but that's my delta. Right now, I saw a change. This is something different than its context, right? Now, 20 milliseconds, you and I go, that's nothing. As a human being, I can't even think of how fast 20 milliseconds. That's fast, right? Certainly not something that's going to make me punch my screen. Not unless I experience it a lot of times. If I experience a 20 millisecond delay once, big whoop, I'm still 31 milliseconds into the trace. It's not that big of a deal. Things are still moving. However, what if I suffer 20 millisecond delay 100,000 times? That becomes real time. That becomes something that hurts, right? Pause my question just for a second. So here I got basically 20 milliseconds, right? Now we notice it is going, or we see which direction is delayed. Now we want to know why. Why did it wait? Why in context, why is it that .2 is just acting and having no problems, and then all of a sudden it waits 20 milliseconds? Right now this is just information. I'm just going to let you know if I continue to scroll this trace file, I'm going to start seeing more and more and more of those 20 millisecond delays. Sometimes they're 18 milliseconds, sometimes they're 20, sometimes they're just around that 20 millisecond range. I see a lot of them. But let's take a look at why. Notice what direction it's coming from. Okay, so the receiver of the data, the recipient, delayed 20 milliseconds before acting and saying, basically acknowledging the last packet. What happens immediately after this delay? If I come down to packet 141, you notice that the server says, great, let's get going again. Boom. In fact, if you look at those 123, 122 microseconds, that is exactly how long it takes to insert a full-size packet on this link. This thing was going fast. And it was ready to start firing traffic again. Going back up to that delay though, if I come over here, let's notice from the receiver's perspective, if I go up just to packet 138, this was an acknowledgement. But this is where something called TCP window size comes into play. All right, this is why you'll notice on my Wireshark, when I've got a profile called TCP plane. That's the one that I'm using right now. I grabbed the TCP window size and I added it as a column up above. Because when I'm doing large data transfer stuff, a TCP window can become congested and slow things down. Now, what is a TCP window? Fundamentally, simply put, it's a buffer. It's a way of me telling, for my receive window, it's a way of myself telling the sender, this is how much space I have that you can send data without acknowledgement. Okay? So every single time I send an acknowledgement, I'm informing you of what my TCP window is. Now when that window fills, I'm basically saying stop send. Stop sending because I'm getting indigestion here. I'm full. I'm not processing this data. So basically it's a TCP receive buffer. So when data is coming across to the receiver, let's take a look at the window size of the receiver of the data. You see the window size value? Now in this case, just so you know, if you know about TCP options, this was not using window scaling. So this number that you see up here is real. So here on the receiver side of things, we only had 2,299 bytes available in the TCP window on the receiver side. That's what it was that's what it was informing the other side, the sending server, the primary server of in packet 138. Well, what happens in packet 139? The server says, all right, you got space for one more frame, one more large one. So I'm going to send one more large one. And then the recipient says, you know what, I got to digest here. It takes 20 milliseconds to clear out that window. And then you see that delay in 140. It responds with a full-size window, 65,535 for those 2 bytes. Again, we're not using scaling. So now the sending server says, great, you got a full window again. Boom. Now let's watch what happens again. Okay, now that we're looking at that window column. All right, I'd like you to keep your eyes over here. So you notice that the sending server, it's got a slightly different size window, 65,160. However, the acknowledgements, the ones that are coming from the recipient, those are the ones I'd like you to keep your eyes on. So if we come down here, the 65,535, that's from the client, that's from the recipient rather. If I scroll down, notice when these window size values begin to drop. Notice right here. So I had a short period of time where the recipient was keeping up with the data as it was coming in. And then you start to see this window size begins to fill. He's sending me data, now I've got room for 64K worth of buffer. He sends 2 more packets, now I've got 61. 2 more packets, now I've got 58. 2 more full size, 55. 2 more, 52, and so on. This window is filling. I'm getting less and less space as I move data. Well, now I'm coming down here, I've got 3567, he sends 1 more full-size packet. Now I'm basically at capacity for any more full-size packets. So now I'm telling that server, I'm full. You got to stop. Again, I see a delay. 14 milliseconds. 14 milliseconds for that server to digest that data into layer 7, let the application take over, or that application come in and scoop that data out. Now I've got more resource. Now I have a TCP window available. Now we're back up to 64. Where are we at? This one's 65,535. Boom, that's when the next data chunk starts to come across. Okay, so right here we see a problem with a receive window with becoming congested. Now there's a few really cool features within Wireshark that can help you to visualize this. Maybe you've seen a TCP stream graph before. What that does is it shows you as traffic's coming in, it shows you the sequence numbers as they increment and any delays that we may see. What I'm going to do, I'm just going to select one of the packets from the server. I'm going to go to Statistics, come down to TCP stream graph, and go to time sequence graph. This shows me the data as it's going from one server to the other. This is the data in flight in one direction. As you can see, it's real bursty. I see a burst wait, burst wait, burst wait, burst wait. Well, those little waits are the 20 milliseconds, the 14 milliseconds, the 25 milliseconds. Like I said, one of those won't hurt you. But when you've got tons, now this trace file was just a sliver of the entire data transfer. These things were happening hundreds of thousands of times. That's what takes a big data transfer from being 15 minutes to 8 hours. And it got worse and worse and worse. So what's the issue here? We have a couple of options. Now I'm not an application developer. I'm not. I don't get into the code, I don't get into that piece. It's just not my strength. I like to stay in my lane. So we can either work with basically the backup software to figure out, is there a way we can tune this TCP window to be processed more often? Or, on the backup application that they were using, there was a teeny little checkbox that said multi-threading. So from the server's perspective, instead of doing this all over one TCP connection with one TCP receive buffer, instead it would open up 20 of them and start blasting traffic down a bunch of different TCP connections, not just one. So I'm not reliant on one TCP buffer to do all this receiving. Now I can have several connections open, each of which have their own TCP receive window. So for us, I didn't want to get into the application code itself. We checked multi-threading. This thing now went in about 30 minutes. Okay, but my point here with TCP, was this a network problem? That works fine. You see packet loss? No. Things are turning around quickly. The network's not dropping the packet. There's no evidence of congestion. This is a protocol thing. TCP is showing us these windows are filling. So that's not really layer 1, 2, 3, and ultimately, we can't say it's layer 7. This is layer 4 filling. It wasn't being processed fast enough as data was coming in. Now there might be some questions that you have about this one, but I got to keep moving with a couple of the other trace files that I have. If there's questions you have, please, after class, please come up or this session, please come up and ask. I don't mind I can even share this trace file with you if you'd like as well. But I really think this shows the importance of knowing when a problem resides in the protocol itself, or we can determine it from that protocol. Okay, let's look at another example. Now in this case, okay, so the thing that we were troubleshooting was slowness. It was taking too long for a certain application to work. And in this case, you see how we see over here, I'm just trying to get this all on the screen for you. You see over here, retransmission. Well, retransmission, what's a TCP retransmission? Simply put, there's a packet that goes, there's a certain amount of wait time, and that packet is retransmitted. Well, my question is always, what happened to the first one? Where'd that one go? Right? Because packet loss, specifically on networks that we control, if I'm in-house on my LAN and I'm not releasing these packets onto a network that I do not control, I don't want to see packet loss. What causes packet loss? What kind of things can come to your mind? What could cause a network to legitimately drop a packet? Could be an interface error. Could be congestion, output drops. We could have some buffer issues on our device along the way, for sure. We'd have errors, FCS, CRC. We could have a link that has a duplex problem, something like that. Those could all cause packet loss.
It could be the receiving device lacking processor or memory to hold the data for the network.
That's a good example. We're actually going to talk about that in a minute. That's a point as well. There's several things that could cause packet loss, right? Now the cool thing about TCP is we can quickly see this. We got those nice big black lines with the red ugly text that shows us, hey, we've got a TCP retransmission issue. Now right away, most of the time, if I see these, is it a server application problem? Or is it a network problem? Where does your knee jerk? If I'm seeing retransmissions, that means data needs to be retransmitted. That means something was lost. If a network is dropping a packet, is that the server guy's fault? Sorry, he's got you. The network is slow. The network is dropping packets. But I want to show you how bad does TCP retransmission, how bad do TCP retransmissions hurt? Well, in this case, you can see we have a client that was connecting to a server. That's the 192.168.1.1. It's sending a TCP SYN. That's the beginning of the three-way handshake. It wants to synchronize to that server. It sends its the beginning of the handshake. It sends its SYN. How long does it wait to retransmit?
3 seconds.
3 seconds. Do you and I feel that?
Oh, yeah.
We feel 3. We're impatient little people.
So with your example here, these are SYNs right? So the server support that the data that is being sent to you, you just not be responding to it, and it's not available, so you get those types of SYNs without being a network issue. So
Now, the comment was, these are retransmissions on the SYNs. So it could be that the server itself, that service, is not responding. It could be a firewall issue or whatever the case is. However, in this case, I've got a whole transaction that worked. Now, in his case, broken, see, if it's a server that's not responding or if it's a firewall, that will never work. All out broken is different than slow. Right?
could be for exhaustion.
It could be. It could be. There's a few things. In fact, we're getting there in the sweet spot. So we see the first packet goes. This is a SYN. We wait 3 seconds. And you notice the second retransmission, that time doubled. 9 seconds. Now at this point, we don't know exactly what the problem is, but we know this is where our hurt is. This is people time. This is pain. By the time I get to packet number 5, or packet 4, where I finally get a SYN-ACK, I'm at 9 seconds. I'm waiting 9 seconds just to establish a connection with that server. All right, so I send the SYN-ACK completes, then we see a get go, we see a response, and then the connection wraps up. Overall, my total connection time is 9.09 seconds, 9 of which was spent waiting on retransmissions. Now, typically, when we see retransmissions, we're going to start to look for any congestion and links, things that are legitimately dropping traffic, especially if we see a full connection. See, the very fact that I have a full connection that did establish, a firewall's not blocking this. And that server is working for some people, right? So that's something that I want to look for. But it's interesting in this case, for this trace file, we actually captured on both client and server. Now, when you're doing TCP analysis, that's a huge thing. That's going to give you a lot of information. If you can simultaneously capture on the client and on the server at the same time, you can tell whether things are legitimate packet loss, if something's being lost in the network. Now in this case, this was a capture from the server side. In fact, that server was tapped, and we were capturing physically on the link that was going to that server. So what does that tell us? And we have a SYN go to that server, we're capturing server side, and we captured that SYN. Wait 3 seconds, we see a retransmission, we captured that retransmission. We're sitting with server side, but there's no network to drop this packet. So what the problem was here is that server was busy. It was handling a lot of different connections, and it ran out of resource for new ones. However, the only way we were able to determine that was by capturing server side and client side simultaneously. Now, a lot of times, I see this less than I do the other scenario, where when we see retransmissions, we're actually talking about packet loss. That's when we say, all right, guys, network guys, we're going to have to go and take a look at where traffic is being dropped. Sorry, the network is slow. Without packet loss, that's a 1, 2, 3 thing. Right? So this is just another example, but I do think it really illustrates the importance of getting that dual-side capture, if you can capture on both. Now for this one, we had to increase resources to that server. In fact, what he started doing was he tuned his load balancer to send more to a different bay of servers to lessen the load on this one, because it was actually tipped. So that was something he was able to do. All right, let's keep moving. How about, if you're in my session this morning, you already saw this trace file, so sorry, you're gonna see it again. How about this one? Now first it looks pretty ugly. We got that black lines across with the red. But let's take a look at what's really happening here. In fact, you know what? I'm gonna hide this. Okay, so client comes and sends a SYN to the server. Server comes back, SYN act. My initial network round trip time. I'm capturing client side for big me. My initial network round trip time, 97 milliseconds. Now at this moment, I don't know if that's good or bad or not or otherwise. Because I don't have any context, I don't have a baseline, I don't have anything to compare it with. All I have is the rest of the trace file or the rest of this conversation. However, 97 milliseconds, if you had a 97 millisecond delay added to a conversation that you were having, is that something that you would cry about? As a human, do you feel 97 milliseconds? Not really. If you feel it once, no. If you feel it 1,000 times, yeah. But the complaint here is that this client was going to go talk to this server. He hit a tab on the application. After hitting that tab, he would see a little spinning wheel. That spinning wheel would continue for a while. And then after a while, it would pop. The information would go. What did they blame? The network. The network's slow. We got to upgrade all of our systems, increase the bandwidth of our circuit. It's all yada yada yada. So we went ahead and captured it. We were capturing it as the client side. We see our SYN act go. We have 97 millisecond round trip time. And then we see our get in packet 4. This is an HTTP call. We're sending a request to that server. And that get was so large, in fact, that the client was sending so much data to the server that it actually spanned more than one packet. That's why you see in the direction from client to server, packet 4 and packet 5, you see the top one, 1514, that's a full-size packet, and the one beneath it is just the remainder. There's so much data to send, it just spanned two, one big one, one small one. So this data goes to that server, and the key packet in this trace file is packet number 6. Packet number 6 tells us it's an acknowledgement. It's from the server. It's coming back to the client. The server got my stuff. It got my get. Those 2 packets that I sent made it there, and the server acknowledged. Now I know He's got my stuff. He's got my request. Now as a client, I can sit and wait. He's got my stuff. Right? I don't have to retransmit it. He already told me he has it. So what do I do? Packet 7. How much time do we wait to kick off packet 7? 45 seconds. That means in 45 seconds we haven't heard anything yet. Spinning wheel. That matches our signal. Now keep in mind they're slamming the network. They're saying the network's slow. They're about to get up their whole infrastructure and start over. So 45 seconds, that's the client side saying, hey, I haven't heard anything from you before I shut down this TCP connection. I just want to know, are we still talking? Did you go away? Mr. Server Link Partner guy? We send a TCP keep alive, which, as its name implies, it keeps the connection alive. Now there's some debate over whether this should be black or not. For me, it depends on what the situation is, because it makes it look pretty bad, right? But actually, this is TCP just trying to keep the connection alive. So that keep alive goes off. Back at 8, we see from the server coming back to the client 99 milliseconds later, an acknowledgement. Keep alive back. Server's still working on the stuff. He's got it. Keep the connection open. Don't worry about it. Layer 7's doing his thing. We're layer 4, let's just keep this connection active. It's not over yet. Okay, so we wait. Now, that 99 milliseconds, that also tells me, you see the delta between the SYN and SYN-ACK? There's my benchmark. That means that this server is about 100 milliseconds away from the client. That's my network round trip time. That's what I'm going to be dealing with. At this moment, that's not my problem. That 45 seconds is. What is that application doing with this request? Well, here again we wait. Back at 9. 45 milliseconds later. Here's another TCP keep alive. Again, I expired my TCP keep alive timer on the client side. The connection timer went off. The client saying, hey, am I keeping this open or are we done? Because if we're done, then we can reset and I can let this connection go. But if we're still talking, you gotta let me know. Packet 9 goes off, 45 seconds later, we hear a response 95 milliseconds later, which is about our network round trip time. Server sitting there says, yep, we're not done yet, keep it open. How far into this connection are we now? 90 seconds. Sound a little similar to the symptom? All right, then we wait. Packet 11. Oh, 18 seconds later, the server comes back with real data, 572 bytes of it. 200 OK, there's my stuff. How long did I wait in total? 108. In fact, there's a cool little timer. If you select a response packet from this server, and if I come down into the HTTP stuff, you see time since request. That's a really sweet little value. In fact, you can add that as, if you're doing a lot of HTTP analysis, you can add this as a column, right? Click it, add as column. Every time you see a request, or a response rather, it'll show you the time since request. A sweet little number. Point is though, I'm waiting 108, over almost 109 seconds just to hear back from the server. Now TCP is helping me understand, okay, they had to keep this connection open. That's what that ugly black is about. However, that isn't the actual root cause. The root cause is that application server, or behind that server, if it's doing any back-end lookup stuff, is being really slow. Now keep in mind, in this case, everything after that, just so you know, everything after that was lightning fast. In fact, if we scroll down to the end of this trace, the whole thing, this whole connection, there's a couple gets. Let's just take this top one though. This is when the data itself is finishing up from the server. and we're at 109.39 seconds. Right, so of that, almost 109 of it was just waiting on the application to respond. So this has nothing to do with the network. The network was fine, no packet loss, no congestion, and no symptoms that indicate that. Here we're dealing with a slow application. Problem is though, from this perspective, we're capturing the client side, right? What I want to know next, where all of our heads should be going, what on earth is that server doing for that 108 seconds? Is it out to lunch? Is it sitting on that call? Is it busy doing other things? Is it doing other lookups? Is it looking for a server that doesn't exist and timing out and rolling back to something else? It does eventually work, so we know it's not completely broken. It's just slow. So the next thing that we need to do from this point is we need to get server side. Now we want to capture server side. Now ideally we captured on both from the beginning, that would have been ideal. Capture server side, now we want to know between that delta, what is that server doing on the back end? What other servers is it involving? Are there any other calls that are bad? Do I have a SQL problem, Oracle problem? Do I have any other type of issue that is taking up that time? Now, sad to say, in this specific example on this project, as soon as we were done exonerating the network, my customer was like, okay, great. I just want to know what's the network. Take off, get out of here. I got the bullet to shoot my application guy. That's all I needed.
It's called mean time to innocence.
Right, exactly. That's a great one. Mean time to innocence. So it's not the network. We're exonerated. Get out of here before I got to pay you anymore. Right. So, but again, TCP walking through this one step at a time can help us to see where that delay is and why it's there. All right, let's look at one more. I think I got enough time. This one was interesting. We had a problem where the symptom was slowness. Full time performance is what I get called for. Clients were talking to a server and having difficulty opening up certain files. They'd start to open up the files, and some of those files would take 30, 40 seconds to open. Now, there was a lot of different sites off this cloud, and it looked like there was just one site that was suffering. All the other ones were working fine. It was just this one. So we analyzed it, and we went ahead just from the start. We had an analyzer on the client end, and we had simultaneously an analyzer on the server end. So we were able to capture both simultaneously while it was happening, while it was breaking. Now these guys were also using WAN acceleration, optimization. That component seemed to be, the configuration seemed to be similar. We didn't spend a lot of time in the network configuration initially. However, just from the trace files, this is a really interesting thing to see. See, over time, it used to be back in the day when we had this client server and there wasn't a lot of devices that would muck with our packets. The packet that you had leaving the client, or the header information I should say, was pretty close to what you saw arrive at the server. We didn't have a bunch of stuff changing it and modifying it, and now with all these different technologies that can change our packets, that's even more reason why we want to have dual side capture if possible when doing TCP analysis. Client and server at the same time. Right? Because there's so much stuff that can happen in the middle. So in this example, let me go ahead and show you some of the details. All right, so this was client side. All right, I've got client. It's connecting to a server. That's the 192.168 box. Connects to a server, sends a SYN. I get a SYN out. Now, how much time? What's my initial network round trip time? Delta time shows around 86 milliseconds. Now, good, bad, or otherwise, I don't know yet. That's just a number that I'm going to put up on my little paperwork. 86 milliseconds. I see the TCP handshake continue, SYN, SYN, ACK. Packet 4, I see a request from client to server. It's 404 bytes long. The next packet down, I see a TCP previous segment lost. Right? Ever seen that in Wireshark? This is where Wireshark, by the sequence numbers, can figure out, see that? Or previous segment not captured. This typically happens one of two ways. Either the packet itself was lost due to my capture method. That's one possibility, meaning maybe I exceeded the capability on my span or mirror, and this packet was just, it existed, but on its way to my analyzer it was lost. Either that, or the network legitimately dropped that packet that was above that 617 right there, and Wireshark figured that out because of the sequence numbers in TCP. See, when it sees this packet 617, it can see, because of the sequence numbers, that there was data before this packet. It can determine that. So I have a packet coming to me. The client turns around and says, okay, TCP do back. It's going to do that because it's sending an acknowledgement for the packet that was sent, the 617. However, it's also going to inform the server, just so you know, I missed the one above it. There's data missing from that. In fact, if you take a look at the info here, not to get too deep into this aspect of it just because of time, but you see the SLE, SRE, left edge, right edge? That's acknowledged data. So what this is the client is telling the server, hey, I've acknowledged in your stream of data that you sent me, I'm able to acknowledge 461 to 2024. However, before that, I don't got anything. That packet's lost. Now, if the server kept sending data past this point, that left edge, right edge of acknowledged traffic will grow. However, it's going to keep sending do backs because it's missing this original packet number 1 that was sent. So the client's saying, hey, I'm missing that packet that Wireshark also says was lost. So I come down here and notice how long in packet 7. 21 seconds. The server waits 21 seconds, and then I see a packet from the server. That's a long amount of time. In fact, in the trace files I showed you before, the first retransmission not only took, what, 3 seconds? The second one took 6? But 21 seconds to wait for a retransmission? That doesn't seem right. If I go down below this is where I can see that things begin to even out, you could say, and traffic begins to move. So what is it about this 21 seconds? In fact, in this call, this 24 seconds you see here, this was a new request from the client. If I take a look down to where traffic stops in that direction, in packet 15, I'm only 21.58 seconds into this trace. 21.09 of which was spent just waiting for this retransmission. All right, there's our spinny wheel. That's where you and I complain. That's when we punch our screens. All right, so what on earth is causing this thing to wait 21 seconds? Well, like I mentioned, thankfully, we captured both sides simultaneously in this example. We captured client side and server side at the same time. All right, so now let's go to the server side. Let's see what it was doing while we were waiting. All right, so this is the server side trace, and I got these two right next to each other. All right, so server side, same connection, same conversation, same request, everything. Client sends a request. We see there's our 32 microsecond of delta time between the SYN and SYN ACK that tells me on server side, right? The network delay. But the ACK comes back from the client in packet 3 86 milliseconds later. That's expected. It's on server side. SYN comes in, I fire off that SYNAC, and then I wait the network round trip time for the final lap. So my handshake, the behavior is the same as it was on the client side. We're just capturing it from a different vantage point now. Next thing happens, packet 4. The client sends a request, there's our 404 bytes, search request. Packet 5. Packet 5 is a large packet, 1514. That's a big one, right? Remember, Wireshark said the packet above is missing. Taking a look at from the client end, taking a look at that 2 back, we can see that there was a large packet that was missing, and the residual that made it. Alright, so that large packet, that's the one, frame 5, that somehow went missing. Let's keep going. Frame 6, this one did make it across to the client. In fact, in packet 7, there's the acknowledgement coming back for packet 6, but that packet is telling me, if I look down into the TCP stuff, it's telling me, hey, I missed packet 5, where'd that go? In fact, if I get 2 of these, if I get 2 of the number 7s, 2 acknowledgements, 2 loopbacks, then I'll just send a fast retransmission right away. Boom. You missed packet 5, here you go, here it was. So what do? I see the acknowledgement come. The sending station, because we're at the beginning part of the TCP slow start, it's still waiting a good amount of time before sending a retransmission. Packet number 8, it waits 3 seconds almost. It sends a retransmission. See how large that packet is? 1514. We're looking at packet number 8 right now. It sends a retransmission to packet, the first big one. Well, what happens here? Nothing. I don't get an acknowledgement for this biggie. So what do? Packet 9, I wait 6 seconds, and I retransmit it again. I get nothing. I don't hear anything from the other side. So packet 10, this is what I call TCP last ditch effort. Instead of sending it as a 1514, it basically slices that thing up into smaller segments and sends it at 590. So now it breaks it down to 590. This is basically, hey, are you still there? I'm going to try this smaller. If not, either you disappeared, the network's gone between us, or I got to shut down this connection. So packet number 10, this is the server saying, hey, here's a 590, 11 is an acknowledgement. If I look at the client side, that 590 came across. Okay, so these big ones, what's the big problem with these big packets? How come they're not making it through? Well, if I take a look at the IP info for these big packets, I've got a little flag here set. I've got the don't fragment bit set. What that means is that's the IP stack on the server saying, do not break up this packet network. If you have a low MTU, if you have anything where you can't fit this large packet through it, drop it. Now hopefully you tell me you drop it, which wasn't the case here. We should see an ICMP wanted to break it up, do not fragment it was set. We should get that from the network. In this case, that was hushed. We didn't receive those packets. So what's our problem? We're not able to get those 1514s across to the client. The small ones are going, but not these big ones. The 21 seconds that you saw on the client side, remember we saw a 21-second delay? If we add all this up, it was a 21-second delay server side. Finally, it sent this 590. Okay, so what's going on here? Why are the two sides, why are we having issues with these large packets? Well, in this specific scenario, the WAS system they were using, the WAN optimization, it wasn't able, because of the junk that they were putting on top of some of these headers, it wasn't able to take large data packets that could not be fragmented. There needed to be some room. So in the routers themselves, they were able to tell TCP for each side, any connection that's established, don't use 1460s. See, the reason why you see 1460 a lot, Notepad, if I got 1460 bytes of data, right? How big is the TCP header itself? It's typically 20. IP is also 20. If you add all that up, that's where I got my little 1500, right? That's why you see 1500 MTUs on a lot of router interfaces. If you take off the Ethernet stuff, the 18 bytes of Ethernet overhead, destination address, destination MAC, source MAC, type, and then FCS. If you take off that 18 bytes, the IP payload itself, there's our 1500 byte MTU. 20 bytes of that is typically IP. 20 bytes of that is TCP. The stuff that I can put inside a TCP payload, maximum would be 1460. I gotta leave enough room for all those headers. Well, in this case, WAS needed more. So in fact, WAS didn't want 1460 to be inside the TCP payload. In this configuration, 1432. That was the maximum amount of data that we could actually send between two TCP endpoints to make room for the other junk. Now, how is that number communicated? Well, in TCP, I strongly encourage you to go to Betty. She's doing the TCP handshake talk on, I think it's Thursday morning here. She's going to go all into that MSS and how it's set and how it's negotiated in the handshake. But I'm just going to show you a quick example where this went wrong and how we found this. All right, so first of all, in the TCP handshake, you see up here, this is the start server side. One of the values that the two endpoints send to one another is this value right here. Let me come. We can see it in the TCP options. You see maximum segment size. This was coming in from the client. Maximum segment size. I'm sorry, it's just out of your view. There you go. From the client, this is in the SYN. It was saying 1460s. We can fit 1460 in each payload. Make room for header space and all that kind of stuff. Now this number is actually between the two endpoints. It's a negotiated number. So if I send you 1460 and you send me 1000, I'll respect you. And I'll just use 1000s. Right? It's actually one of the very few things that's negotiated between the two endpoints. So right now the client says, hey server, I'm using 1460s. The server sends back in the SYN-ACK. Let's come back down to that value. Okay, client. Now this is the SYN-ACK that we're looking at. Okay, client, great. 1460. Let's go ahead and fill up these packets. Let's use the full payload. All right, SYN-ACK. Let's take a look at the SYN-ACK from the client end. If we come in here and take a look at the client, going to come up to the handshake, SYN-ACK from the server, going to expand TCP, going to come down to MSS, when the server sent it, that trace file I was just looking at, we were server side. We received 1460 and we sent 1460. That was our maximum segment size that we agree on. In flight, along the way, something changed. Something decremented this MSS value, maximum segment size that you can fill your payload with, down to 1432. So the client, right now, remember this is negotiated. The client's going to say, great, I sent you 1460, but you sent me 1432. Let's go with you. You win. Good. So I'm not going to send you a packet with more than 1432 in the payload. Right now, that's what the client thinks. However, what does the server side think in this connection? 1460. The server is still thinking, this is awesome. We got full-size packets. Let's fill them up. And that's exactly what the server did. So the client right now, it's 1432, like you mentioned, there was some stuff they had going on where they needed some of that room. But the server, it was basically left out of that part of the conversation. So what does the server do? It begins to send large packets with do not fragment bit set. Don't break this up. MSS said we could handle it, at least from the TCP layer. So let's go ahead and use these big ones. It sends a big one. That packet gets dropped. It sends another big one, dropped. Another big one, dropped. Fine. Let's go down to the small TCP segment of 590. All right, so what was happening here? What was causing this? Well, coming into that network configuration,
Is there a window update? TCP window update?
the window wasn't the problem. The window update would have been from, hey, my window was full, I was congested, but now I'm full. Now I'm fine again. But the window is just a separate component of what TCP is doing. But good thinking. And this specifically wasn't a window thing. This was an MSS thing. Let me show you why. On the client side, can't remember if I copied this. There we go. I just asked them, I said, is there anything along this path? What is it? What device along the path is decrementing that MSS in flight? There's some network device. Whenever you see that much change in your headers, something's mucking with it. Somebody's changing it. Who's changing it? And let's go talk to that router. Well, in flight, they told me they went in and pulled the router configs, and on the client side, this router config was set to any inbound packet. It would decrement from 1460 down to 1432 for the TCP MSS. And then it would send that TCP signal to whoever requested. So it was being decremented server to client, that direction. So the client never would have sent a large, full-size packet, would have only filled it to 1432. However, I asked them, okay, what's going on the other direction? Nothing. That configuration is not there. Okay, just curious. In all the other sites that don't have this problem, are you guys doing outbound? Are you decrementing MSS outbound as well? Well, I don't know. Let's go find out. Oh no, we are. Okay, so let's go ahead and see what happens if we just have this configuration match the others and go ahead and decrement the outbound MSS to 1432 as well. We add that change, problem goes away. The reason why is because the SYN, when the client sends a SYN, as soon as it hits this router is going to go, nope, we're not doing 1460s, we're doing 1432s, here you go server. And as soon as that happened, the server would respond with a TCP SYN-ACK of 1432. It doesn't even suggest 1460. It's like, fine, 1432, we'll play your game, we'll keep it small, we'll let the WAN optimization do its thing. So basically what happened is they set this in the wrong direction. Once this happened, now we had the proper size set both ways, and now we weren't seeing these larger 1432 bytes or packets dropped. Okay, so back to our OSI model. Who owns this one? This is a network problem, a server problem, an application problem. Welcome to our world now, right? It's ours. We're going to take control of the transport layer, right? And it's things like this. It's understanding what TCP is doing with these little facets of how it works that becomes so important given where we're at today, right? So definitely something that we want to keep tabs on. Okay, so those are the trace files that I have for you. What I'm going to do, I'm going to go ahead and end the session early. If you have questions, you can come up and ask. I'll be here for you. But I hope your takeaway point from this is just a few of the examples that I've come across in analyzing TCP and some of the things that have made these little nuances of TCP important. So continue to study TCP, embrace it, hold on to that OSI model layer, make it yours, because you're really going to be able to understand problem domain isolation a lot better. Thanks for attending, and we'll see you guys soon.